All right, afternoon, everybody. Thanks for joining in. Looks like we got good turnout for this. So I guess it's a good thing that we scheduled this topic. So I'm pleased to introduce Kapil Agrawal. He is going to be going over Kubernetes networking for infrastructure engineers. If people do have questions, certainly use the chat room. But Kapil said that we can answer a lot of the questions at the end unless you have something that's really relevant, and then I'll interrupt them to get the answer. So we'll turn it over to you, Kapil.
All right. First of all, audio check. Jason, can you confirm?
Yep, perfect.
Perfect. Awesome. Thank you. Hey, folks, thanks for joining us here today. My name is Kapil. I'm a security engineer with ESnet. Uh, okay, yeah. I'm a security engineer with ESnet. I am also a recovering network engineer and a former OpenStack admin, and that's how I ended up doing Kubernetes networking and security. So back in my last job, I got introduced to OpenStack, and we had users who were running Kubernetes on top of OpenStack, and so the network abstraction became a nightmare. And so, in order to debug, in order to work with them, essentially, we had to go deeper into the stack. And as you know, like ESnet likes to run IPv6 only network, but this talk is not about IPv6. So the inspiration for this talk is coming from the lessons we actually learned from deploying Kubernetes in ESNet's IPv6 only network. Why? Because deploying Kubernetes in our IPv6 network, V6 only network, that became a forcing function for us to go deeper into the Kubernetes network stack. All right. So uh, I'm assuming people on this call have at least heard the word Kubernetes and what it is, but in general, it's a composable system. It's you can pick and choose some of the components that Kubernetes has to offer and build your own distributed system. Long story short, there are two main components that make up Kubernetes. One's the control plane and the other one's the worker node. Node being, again, when I use the word node throughout this talk, node generally means like a VM or a bare metal where you're running a systemd process. Let's just put it that way, right? So you have control plane, you have worker nodes. There are some important components that make each of those roles essentially. So on control plane, you've got a generalized, a very generic API server that runs, and then followed by an etcd key value store. The key value store is the one that is responsible for holding the state, the desired state of the applications or of the cluster in general. Then you've got the kube controller manager, which is responsible for doing the reconciliation process. Followed by there's a very important component that runs inside the cluster that's called core DNS. And what that does is it does DNS and service discovery. It's like internal DNS for the cluster, essentially. And why we need that, we'll get to that in a bit, but bear with me for now. On the worker node, what makes a worker node is a process called kubelet. Kubelet is the process or the agent that runs on a node or a worker node that connects to the API server, and it watches the resources of the changes happening in the API server. And then kubelet is also the agent that invokes the container runtime. So if you've heard of Docker-D, for example, if you heard of Container-D, for example, if you heard of CRI-O, those are the container runtimes that kubelet is compatible with. So, and then there's another optional agent called kubeproxy. Again, kubeproxy is optional in the sense because kubeproxy is the one that is responsible for providing for doing the internal plumbing for your containers, for your pods that run in the cluster, so that traffic coming in and out of the cluster basically gets forwarded using it. It programs the IP tables data plane essentially to push packets through the cluster nodes essentially. And then what makes Kubernetes composable more or less is because of the plugins. There's an add-on system. You can pick and choose to a certain extent what storage interface you want to, what storage plugins you want to use. You can use Ceph or and whatnot. CRI, as I mentioned, container runtime interface. You can pick and choose to some extent. Like you can use Container-D, you can use CRI-O, you can get runc. I believe, and there's one more who I forget what its name. But those are typically the ones. The Container-D is the most common one that you would use, like by default. CNI, that's the part that we're going to talk about today. Container network interface. Okay. So high level, at a very high level, if you think about Kubernetes, I would say it's a 3-layer cake, right? Where the first layer is the underlying network infrastructure. And what I mean by that is, so before you set up a cluster, you have to have before you install the Kubernetes, the daemons and whatnot, you have to have a VM, a node, right, a bare metal. That node to node connection, you need to have node to node connectivity. Basically, the connectivity from one node to other node and node to world or node to your container registry, perhaps. So that's the fundamental requirement, underlying network infrastructure. But then after you do that, you install Kubernetes, but before you do that, you have to plan for cluster networking. How are you going to provide connectivity for pod to pod, pod to world, right? Because at the end of the day, pods are what makes pod is the fundamental atomic unit of compute inside Kubernetes. We don't run an individual container in Kubernetes. We run pods. Pod again is there is no such thing as a pod in the Linux kernel, right? As you all know, pod is just an abstraction over namespaces. And the abstraction is again well defined in the Kubernetes API server. So as a user, you don't interact directly with the namespaces, the Linux namespaces. You don't interact directly with the pods that are running on the worker node. You interact with the API server. The API server has an understanding of what a pod is essentially. And the last piece, the third and the final cake is the service networking. So let's say, okay, you've deployed your, underlying network, you've deployed your infrastructure, you've deployed your applications, and so now you have pods, you've got pod-to-pod networking, going and whatnot. So what provides pod-to-pod networking? First of all, it's the CNI, Container Network Interface. It's the plugin that you install in the cluster. That is what is responsible for providing the pod-to-pod and pod-to-world connectivity. For service networking, again, then comes the part of, okay, well, you've got your pods deployed in the cluster, you've got applications deployed in the cluster, but now you have to be able to access the applications somehow, right? So because pods by nature tend to be ephemeral inside Kubernetes. So there has to be a mechanism for being able to access these services or the applications these pods represent through a stable IP address, through a stable DNS name. That is where services come into play. Kubeproxy, as I was mentioning in my previous slide, is the agent that runs optionally runs on each of the nodes and provides the load balancing, provides the I would say a stable internal virtual IP, a virtual name for your collection of pods that are representing a service. Okay, now here comes the CNI. Okay, so CNI basically is technically it's a specification. So anything when we talk about CNI, CRI, CSI, right? Each of them have the word interface. Now, any of you who have any of you who are victims of Java or perhaps Go know what the word interface means. Now, Kubernetes and the cloud native ecosystem entirely is written in Golang. So of course, the word interface over there essentially means a contract, a specification. And so CRI is a spec, CSI is a spec, so is CNI. You can actually go read the CNI specification if you go to cni.dev. So what does CNI actually do? It actually handles IP address assignment for pods and also handles the plumbing for pod-to-pod connectivity. And how does it do that? So there are multiple approaches that CNI, again, this is very implementation specific, but there are multiple approaches how pod-to-pod connectivity can be achieved. One of the common approaches, well, you just provide VXLAN tunneling between, or I guess your CNI provides VXLAN tunneling between your nodes, and that's what the pods use to connect from one node to other node, essentially. Or you use some kind of encapsulation technology, other encapsulation technologies like Geneve or IP and IP. Or the other approach, the I would say scalable approach is use native routing. The fundamental requirement over here for pod-to-pod connectivity is each pod in Kubernetes must have a unique IP address, right? And so, and again, these addresses tend to be ephemeral. So that's it. What the native routing approach does is think of it like you're just think of it like you have a you just have a container running on your machine that is that is routable across your underlying network. That's the simplest way to explain that, I think. So there are some programs. So what it does is essentially it programs some kind of a data plane. CNI in general programs some kind of a data plane to push packets. whether that is your net filter subsystem, and it will basically program your it will program your netlink, your routing table in the Linux kernel, so that your routes get plumbed from your containers, your pods, from your pods, from your namespaces to the root namespace and follow on, and from there on. Um, or you use something like, or advanced CNI such as Cilium, um, they basically use eBPF to push packets. So then there is another emerging way to do data plane, which is called VPP. That is, I think, supported by Calico. The most common examples of CNI are Cilium and Calico. At ESnet, we use Cilium, although this talk is going to be CNI agnostic as much as possible. Okay, so I mentioned the word kubelet in my previous slide over here. So let's go back once again to the previous slide. Let's look at the diagram. So we've got kubelet over here. Kubelet talks to the CRI plugin. The CRI plugin is what invokes the CNI plugin. It's a function call, right? It uses underneath the hood. If you look at the specification, all of this is just RPC, remote procedure calls. And implementation-wise, it uses gRPC under the hood. So you've got a kubelet. Kubelet is the agent that connects to the API server and watches for changes happening in the API server. There we go. And how does it do that? Kubelet actually has an agent. It's basically a API watcher. And what that does is it watches the persistent connection. It has a persistent connection going to the API server. And over there, it basically watches for any changes happening in the API server. The API server has a constant, I would say, API server is up to date about constant changes happening in the entire cluster, because all the changes that happen in the cluster are recorded in the API server, essentially. Okay, so then the kubelet has a sync loop, and that's where it listens for events, checks the desired state, compares with actual state, and executes actions. Execute actions for what? For create, read, update, delete pods. And then kubelet doesn't do that by itself. It calls upon, again, through a Unix domain socket to the CRI, container runtime interface. The container runtime interface, which is like, for example, you've got your container D, you've got your cryo and all those things, right? Then the CRI essentially invokes the CNI underneath the hood. The CNI again is the container network interface such as Cilium, Calico, and the CNI has its own configuration. Again, the implementation specifics of each CNI can be different. As I said, it's an add-on system, it's a plugin system. While they all adhere to the same specification, they all have their own features, so as to say, right? But at the end of the day, when the CNI is called upon, here's what it does. It creates a network namespace. This is where rubber meets the road. And the network namespace that is created for one pod has its own network namespace. Or I should say, a pod can have one or more containers, and all those containers running in the same pod. One pod gets a single network namespace. And of course, one pod gets like that network namespace is assigned to that network namespace gets assigned a unique IP address, essentially. So if you have multiple containers running inside the same pod, how do they communicate? They communicate through localhost, so that they can traverse the localhost or TCP/IP stack. Okay, so before we as an admin, before we even go deploy, before we even go think about deploying Kubernetes, right? There are a few things that we have learned through our operational experience that we need to plan for, right? One of them being the node CIDR. What do I mean by node CIDR? This is the address for the underlying infrastructure. That is your control plane nodes, your worker nodes. This is again like subnet planning, right? Typical network subnet planning. Pod CIDR, cluster CIDR, those are something that you have to plan for. And the reason why I say we need to plan for all of this is because it's fundamentally required that the addresses should be non-overlapping. And because Kubernetes is a composable system, depending on the components that you pick and choose, the defaults that those components ship with, there is a good chance that there might be some overlap in addresses between what one component assumes that you're using versus what the other component that you assume that you bring in. So just like that goes without saying, don't just rely on the defaults. Yeah. Pod side or service side, so we have IP addresses for the pods get assigned by the CNI. Addresses tend to be ephemeral. Service side, that is service side is I would say a cluster IP only service that is reachable from only inside the cluster. It's ideal for microservices, internal microservices connectivity and whatnot. So and then you have the ingress sider. So let's say, for example, if you even expose your application, like let's say you've deployed your application, right? You've deployed your application, you have your pods going on, and then you want to expose your pods to the end user. I mean, at the end of the day, you have to provide a stable IP and a stable address, right? For those, for even if the pods are ephemeral. So what Kubernetes does, it has a concept of something called a service. And that service is an object. Essentially, it's an API object. That service is just a name and an IP address, like a DNS record, right? What you do is you associate the service name with your ingress, essentially. Okay. There are some traffic patterns that one needs to be aware of as well when we are designing the cluster. Traffic patterns such as north to south and east to west. So north to south, as in, so when user is trying to connect to an ingress IP for an application running inside the cluster, could the traffic pattern could also be something around something about like when a pod is trying to connect to the world, or perhaps node is trying to connect to the outside world, right? If node wants, if the kubelet is trying to pull a container image from a container registry, that is the traffic that goes from node outside. That's an egress connection, right? East to west. That is, so like, for example, let's say you have a cluster and now your one node needs to connect to the other node internally. That would fall under east-west traffic. You have pod-to-pod connectivity, pod-to-service connectivity. Pod-to-service connectivity, again, how does that work? So when a pod connects to a service, as I mentioned, a service is something that has a stable name and a stable IP address. So that service essentially gets resolved. That service name essentially gets resolved to a stable IP address that is provided by the internal DNS server. That is called DNS. And so that's how pod gets to connect to a pod. That eventually translates to a pod-to-pod connectivity, essentially. Okay. So again, this is just an example. While this diagram represents like pod-to-pod connectivity, the actual implementation will is highly dependent on the CNI that you're using. So for instance, in this over here, what we have is we've got we basically have two pods. Pod one has, let's say, as I mentioned, like a pod can have one or more containers, right? So in this instance, for example, we have one pod that is running two containers. How do those two containers communicate with each other? So typically, if you've heard of sidecar pattern, this is what happens. When you have your main application container and the other sidecar container runs alongside of it, they share the same network namespace. What does that mean? They also share, like, as in, there is no isolation at that point. Like below this point, there's no abstraction, no isolation whatsoever. If container one and container two are sharing the same network namespace, and let's say, for example, if container two gets compromised, at that point, like container two or the malicious container will be able to snoop in all traffic and see everything that's going on inside the namespace. Okay, so now if pod one needs to communicate to pod two, that goes over. At the end of the day, what happens is from between the pod network to the root network namespace, that there's a vEth pair, right? Virtual Ethernet pair. That vEth pair is plumbed again by the CNI. So you've got, as you can see, like through the step number one, the traffic goes from your pod network namespace to the vEth pair, followed by there's a virtual bridge that gets set up. That virtual bridge, essentially, this is again happening inside one single node, right? So if you can have like multiple pods running on one single node. So this is, I would say, intra-node connectivity for pod-to-pod traffic, essentially. But now what happens when you have, let's say, a service? I keep talking about service, right? So service, again, is a loaded term, I understand, and it often causes confusion. The purpose of a service, the whole point of a service is to provide some kind of stable identity, right? Like a stable name or a stable IP address to a set of pods. These pods are going to be ephemeral in nature. So when we keep talking as security, like when we keep thinking about, well, we treat IP addresses as our identity. That concept doesn't work in Kubernetes because IP addresses in general are meant to be ephemeral. So what gives you the identity in that instance? Your identity comes from the service IP, the service and the VIP. Essentially, those are the stable things. Okay, so how does the traffic flow then from your cluster IP service? Um, so like there are mainly three types of services in Kubernetes: cluster IP service, node port service, followed by the load balancer service. Um, Again, these are a bunch of names. What do they mean? What that means is you have actually at the end of the day, when you receive a packet, right? When your pod receives a packet, or when your pod wants to transmit a packet, your packet essentially goes through the virtual Ethernet pair, followed by, so if I go back in my previous diagram, your packet actually goes from the ETH0, followed by the virtual Ethernet pair, followed by ETH0 on the root network namespace, so as you're seeing on the node, right? And then it traverses, and then as it's going through that stack, it goes through a chain of IP tables, NF tables, as you can see. This IP tables is managed by two things. One, it's managed by your kube proxy running on the node, uh, kube proxy agent running on the node, but then CNI, container network interface, also has a role to play over there. The CNI also manages parts of the IP tables. And speaking from operational experience, this is part of the reason uh, why modern CNIs like Cilium, they've gotten rid of kube proxy in general, is because because of the performance degradation that comes with using IP tables, and also the fact that if let's say, for example, you are an operator and you end up doing, like you make an IP table change on your host and you reload the IP tables, boom, your entire cluster network is broken now. Um, so the alternative over there that the modern CNIs are moving towards is to use eBPF maps. Cilium uses eBPF as the data plane. It does not use IP tables. I mean, it can, but with kube proxy replacement, Cilium uses eBPF maps. Okay, again, more on services. So let's say you have this is very similar to what I would say like a load balancer in general, like a concept of load balancer in general, right? Which is, so let's say you have a load balancer, and that load balancer is sitting in front of your backend nodes, backend VMs, backend services, what have you. Anything that happens in the backend is ephemeral. The load balancer is what provides you a stable VIP, a stable virtual IP. That's basically more or less what the concept of a service is, except the service is a abstract concept in K8s essentially. And the service plumbing happens at, like I said, in the IP tables layer using kube proxy. So there are there are generally three types of services: cluster IP, load balancer, and node port. So with cluster IP is typically used where, let's say, you have an internal microservices running within your cluster. That's the default service type. Load balancer service is something that, let's say, you have an external load balancer, for example, or perhaps you're using BGP. Like at ESnet, we use BGP for doing load balancing and also for exposing our applications outside the cluster. Um, so what you do is you use BGP, or I guess you use the load balancer type service to provide a external IP address for your application. You provide an external IP address, and then that is what gets associated with the DNS record. But at the end of the day, when the load balancer, as you can see, there's a red line going from load balancer object to the service object. So at the end of the day, when load balancer sends traffic back to uh, the service, what is that service? That is the cluster IP service. So at the end of the day, load balancer, even then, when it sends traffic back, it gets translated back as cluster IP. And then there's a node port. So node port is typically used in environments where, let's say, you have an external load balancer, like a physical appliance or something, and that appliance needs to connect to some sort of VM, some sort of nodes that you're running, and those nodes are running a bunch of cluster IP services and whatnot, right? And so in that instance, what it does is you install an operator of some kind on your cluster, and that operator connects to your external load balancer. Your external load balancer now, which is essentially a plugin, more or less, right? Your external load balancer now, when traffic comes into your external load balancer, it knows, okay, well, uh, the traffic coming in is going for myapp.example.com. It knows that, okay, well, myapp.example.com is available on this service IP, this particular node port per se, right? So it sends out that traffic to one of the VMs running, to one of the backend nodes or VMs running on the behind the scenes, and the packet gets forwarded to your cluster IP eventually. So the catch over here, the interesting thing over here about node port though is, one second. The interesting thing about node port over here is that it uses a random range. So it will use a range from 30,000 to 32,000 or what have you. 32767, I think it is. Yeah. And so if you do see like random ports opening up on your VMs or on your nodes, you'll typically see that as node port range. That is called the node port range. Okay. Service discovery flow. So as I was talking about service discovery, so what is the most important component essentially in the cluster that performs service discovery? It's this component. Hold on, let me highlight. Yeah, this guy here, cluster DNS, core DNS. So how does that work? So what you have here is when let's say a client pod, you have multiple applications running inside the cluster. And so one application then now requests the IP address or tries to access another application running inside the cluster. So as I mentioned, the IP addresses tend to be ephemeral. So in that instance, well, how does the client, how does a pod one know which address it should reach out, which like when you're sending out a packet, how do you know the destination IP in that case, right? I mean, because the IP addresses can change over time. So that's where service discovery comes into play. Also, you'd be wondering, well, why do you need to run a core DNS? Why do you need to run cluster internal DNS? Why can't we just use Bind9 or like Power DNS or what have you? So core DNS actually does not actually watch the pods or the network itself. It tracks the Kubernetes API server. And that's what makes it special because it has the ability to understand the Kubernetes specific idioms, the Kubernetes specific the Kubernetes specific objects, and it has it implements basically a controller right inside the process that uses a watch API to monitor two specific Kubernetes resources, that is services. And by services, what it does is it maps service names to cluster IPs, right? And it also watches for endpoints. The endpoints is basically this is what maps your pods to your current IP addresses, right? So if you go inside core DNS configuration, you're not going to find any like if you go inside core DNS zone file, for example, you're not going to find any A records, quad A records, CNAME records, TXT records whatsoever. What you will find is basically just a blank zone file, and the core DNS uses the Kubernetes plugin to talk to the API server and fetches that information which is the mapping between service name followed by the endpoints. That's it. That is long story short. That's how service discovery works in a nutshell. Oh. Okay, so pod to service. So when let's say you have let's say for example traffic pattern that we have in this instance is we have pods, and then these pods are going to connect to an internal service. Let's say you are running a front end and a back end. Your front end pods are represented by a different kind of service called front end service. Your back end pods are going to be represented by a different sort of service called a back end service. Let's say user sends a request. The request goes from front. The request now ends up on a front end pod. Now the front end pod needs to connect to one of the back end pods, right? There can be multiple back end pods. So in that instance, how does that traffic work? The way that traffic works out is your pod essentially will connect to your traffic going from your pod will go out through this vEth pair, right? And based on that, again, based on the DNS lookup that goes through, the DNS lookup, the service discovery process says, well, I need to connect to the backend service. So backend service will resolve into one of the available endpoints in the cluster, and then followed by goes through the vEth pair, goes through a routing lookup process and whatnot, right? And that's how it goes on the other side of go to the other node and wherever your one of your backend pods is available. Could be on the same node, could be a different node. So pod to service, basically pod to service traffic pattern is no different than pod to pod. The only difference over there is your service name, your service IP, your service name gets translated through the service discovery process. And then eventually that just becomes pod to pod traffic. Yeah. Okay. So then the other traffic pattern that we have here is ingress traffic. So how does that work? So in ingress traffic, let's imagine you are a user somewhere over here, somewhere over here. The user sends traffic to the load balancer port, right? To the load balancer service. Load balancer service again is the one that has an external name, an external IP, and has this is what is associated with the DNS record. And so this traffic, this load balancer object, now based on one of the load balancing algorithms, could be round robin or could be something else. The load balancer then determines, well, if you're using BGP, for example, your load balancing algorithm becomes ECMP in that instance. So based on that, it determines that, well, I need to send packet to one of the nodes over there, right? So it sends to one of the nodes, it goes through the lookup process over here, the lookup process, and based on that, it eventually ends up on the destination pod. So again, the question comes, well, how does the load balancer know which pod I need to send packet to, essentially? All of that boils down to you have a load balancer IP address. That load balancer IP address somewhere in the stack, somewhere in the cluster, right? Whether that's on the load balancer or that is on the individual nodes, there's a map. There is a mapping of here's a load balancer object, and this load balancer object has one of these available endpoints, essentially. Or this load balancer object is mapping this cluster IP service. And that cluster IP service, of course, is going to be fronting a bunch of pods. So actually, for as far as slides go, this is all I have. But what I do want to show is some of the tools that we use at ESnet to gain more observability inside the cluster. I would like to demonstrate a service discovery process using Hubble. So as I mentioned, at ESnet we use Cilium CMI. So if I were to do and what we're seeing over here is a cluster that is running at ESnet. This cluster is running in an IPv6 only network, but again, that has nothing to do with IPv6 in general. So there's an observability tool that Cilium comes with. It's called Hubble. And with Hubble, we have the ability to basically gain more visibility inside traffic that is going in and out of the cluster or what's happening inside the cluster. It's an excellent tool for debugging. So if we were
Kapil, could you make your text a little bit bigger? It's hard to see that.
Oh, sorry, my apologies. One second. How about now?
It's a little bit better. Thank you.
Oops. Okay, so if I were to do kubectl get pod -a. So again, just an example, we have a server, I'm running a cluster over here at ESnet internally, and this is an IPv6 only cluster. But again, even if it's an IPv6 only cluster, it has nothing to do with IPv6, like what I'm about to show you. So kubectl exec, I've got a netshoot pod running. And then in the other tab, what I'm going to do is I'm going to say Hubble observe -b follow demo. Okay. So the other interesting thing that we have here is kubectl get service. As you can see, in the cluster, we have a service. This service is called Hello World service. This is a cluster IP type service. Has a stable IP, which is a ULA address, right? And it's available on port 80. Now, if we were to do kubectl describe svc -n demo hello world, what we see here is a list of endpoints that are associated with this service, right? Here's an endpoint, and here's the other endpoint. So now, how does the traffic flow actually work? Let's look at that. So I've got Hubble over here. Think of Hubble like TCP dump, but TCP dump that understands actual Kubernetes idioms, right? Like actual Kubernetes concepts. Like TCP dump in general is great, but it doesn't have concepts of API server. It doesn't have concept of labels, selectors, annotations, and all the metadata that is important that is important for debugging anything in K8s. So if I were to do curl hello world, right? Now, what is hello world? Hello world is the name of the service over here, right? So if I were to look inside my netshoot pod running in the same namespace as my hello world service. Yeah, let's see resolve.conf. So netshoot, for those who are not aware, netshoot pod is basically a really nifty uh, container image that is available that you can pull in your cluster, run in your cluster for, and that contains all the debugging tools, all the troubleshooting tools that basically you need to debug anything network related. So as you can see, like even if I run, for example, curl hello world, my cluster DNS punches in um, this search string inside all the pods that run in this namespace, right? And so if I were to do hello dash, there we go, generated, there we go. So clearly the curl return like status, I got a status 200 and all that, right? Curl return some data and whatnot. So let's look at the traffic. Let's observe the traffic that we just received over here. So as you can see, traffic was sent to core DNS, right? Why? Because it needs to resolve what hello world is, essentially. So, and we got return traffic from, we got some return traffic from core DNS, essentially. Then what we got was, okay, well, here begins the actual traffic for like synac, the song and dance, the TCP song and dance, followed by some data, that went back and forth, followed by an final acknowledgement. So now again, would it be much nicer to receive more information? Sure, we can do that. So if you do -o JSON, again, this is a fire hose of information. And when I keep running this in my terminal crashes because it usually cannot handle the level of information that we receive. Let's run the same curl command on the left side. Oops, what did we get here? We got a bunch of JSON data. And if we inspect one of the JSON blobs, what do we see here? We see, let's scroll up. Okay, what do we see here? We see here, okay, so source IP, destination IP, all that stuff, great. But what do we also see? Here's the important part, the namespace information. This isn't something you're going to get in TCP dump. The labels associated with it, right? The source, the pod name is associated with it. Destination, right? What's the destination? So again, what is this identity thing again? The identity, so as I mentioned, in K8s, if when we talk about, okay, well, what is an asset, right? So we typically treat IP addresses, IP addresses are like assets, so that we punch those addresses inside our security scanner or whatever. We punch those assets in our IPAM and whatnot. That model doesn't scale in Kubernetes. What you have here is an identity. This identity is derived from your set of labels. And so Cilium has a concept of identities and assigns this identity, unique identity to per application. And this identity is stable. This identity sticks with the application throughout its life cycle. What do we also have here? We also get what's the name of the node where this traffic came from, right? What do we also have? Let's see. Traffic direction, egress, to network, trace reason. Is this a reply traffic? No, it's not a reply traffic. So yeah, more metadata, I guess. Then there's also another component that I would like to share here. So let me go to browser. Let's go and open up. Oops. Give me 1 second. I'm trying to open up the ports and whatnot. localhost 8000. Okay. So what this component is basically a web UI for Hubble, which I was just demonstrating. So if I were to go, oh, well, I'm on Safari, that should be fine, I think. So like, for example, if we were to go and say, show cluster-wide data. Yeah, it's doing that because I'm on Safari and it doesn't like Safari, but I can see the same, we can see the same thing in Google Chrome, for example. But look at this, for example, like we have traffic that is being forwarded, that is being dropped, and then this is basically an observability tool that gives us the visibility on what's going on inside the cluster. All of this is exportable through, as I said, like it returns JSON data, so you can export that to your favorite collector, like Splunk collector or what have you. Yep. So if I were to say don't aggregate the flows, it shows even more data, basically. It also creates a service map of what services are running inside the cluster, which is not very visible. I realize that because I am using Safari. Let me open up Chrome here real quick. Localhost 8000. This should be better, I think. Show cluster-wide data. Okay, there we are. So this is basically service discovery playing out, and it discovers what services are running inside the cluster. And based on that, it creates a map of what's talking to what. Similarly, if we want to filter down to a single namespace, like for example, demo namespace, right? And now what we're going to do is we are going to go and generate some traffic. Let's go to demo namespace, generate some traffic. Let's go back to there we go. We now have a map because the discovery process worked. And based on that, it created a diagram, created a nice diagram that says, okay, well, we have a demo namespace. And so over here, we've got a demo service. Sorry, we've got a hello world service, right? That is listening on port 80 TCP. And then this demo namespace over here also tried to connect to world 80 TCP. What is that traffic that is trying to connect to the bunch of drop traffic? That's interesting. That seems something that is worth investigating. Looks like it's trying to connect to a ULA, a link local address. Interesting. Yeah. So that should give you an idea of like what kind of observability we can get from in and out of the cluster. I see a hand raised, I think. Stefan, yes, sir, go ahead. Stefan, is
Whoops,
this?
that's my fault. Hold on, let me. They changed the Zoom features on me. Hold on 1 second. Try again to unmute yourself.
Hey, it looks like it works. Thank you.
Yes.
Yeah, Kapil, just curious, is this dashboard that you're looking at, is this Hubble in the
Yes, this is
UI?
Hubble.
Okay,
Yeah.
thanks. I missed that part. Thank you.
Yeah. So if I were to go in the overview section, all it says over here is Hubble nodes, right? And yeah, that's what it says. So the connection part is interesting. Sure, you can see a lot of connections. You can visualize, what's going on with specified flows and whatnot. But the most important point to me as a security engineer is this section. Um, you can actually go create a network policy for yourself. And to do that, typically what you have to do is, well, you have to learn some like, special DSL or whatever, like, okay, well, how do I create a network policy? And what's the syntax? How do I restrict traffic? How do I allow traffic, and all those things. So in the zero trust world that we live in, essentially, you can actually apply namespace isolation using this UI. Essentially, like it won't apply your policy, but it will give you the YAML manifest that you can use and check that into Git. And also, if you're not using Hubble, for example, but you still want to like play with it, there's a website called Network Policy Editor. Network Policy Editor. If you go here, let me put the link in chat. Where is chat? Yes, Zane says, I do see enterprise UI is being displayed here. That is correct. Yes, sir. We are this UI that you're seeing is the enterprise UI, correct? The Hubble Enterprise UI. The open source version of Hubble UI does not have does not have this network policy editor built inside it. But other than that, you can still see connections. You can still see service discovery map. You can still see flow verdicts and all those things. Yeah. But if you want to do but if you want network policy editor without using the enterprise version, you can go to this website editor networkpolicy.io. So there's another tool that I would like to show over here. If you go to ebpf.io, if I can type. Oops. Oh, looks like their cert expired. ebpf.io. I mean, this was the website. Their cert expired. Oh, that's embarrassing. I have to poke those guys. Okay. Anyway, but there's what I wanted to show is there's a marketplace of eBPF tools for debugging and troubleshooting. And that is something that you can find on ebpf.io if their certificate works, when their certificate works, whatever. But then there's other tool that I've been using that I've been playing with called Inspector Gadget. Put this in chat too. Okay, what it does is it uses the power of eBPF essentially, and based on this tool, you deploy gadget, you deploy Inspector Gadget in your cluster, and when you want to debug, you essentially say, "Hey, use this particular gadget." And what are the different types of gadgets that are available? There are different types of gadgets available, such as there's one for trace SSL. So if you want to trace SSL connections, you can do that. There's one that's trace DNS. This is somewhat similar to Hubble, but still not Hubble. And what that does is what this tool does is it depending on which gadget you're using, it will dynamically inject eBPF code and attach some trace points and hooks in the Linux kernel at certain points to give you the information that you need. So for example, you can select TCP dump, and it also allows, the nice thing about this is it allows you to run TCP dump, but using TCP dump with kubectl specific, with Kubernetes specific metadata. So like you can say kubectl gadget run, and then followed by labels, selectors, so and so. There's another tool very similar to Hubble that is CNI agnostic. That's called Retina by Microsoft. As it says, integrates with Cilium's Hubble for additional network insights such as flow logs, DNS, etc. And it's also something that can do things very similar to TCP dump essentially. So if you go to their website and if you look for CLI setup Retina config, I was going to show you captures. Hubble UI, yeah. So you can basically use Retina as the you can basically use Retina as the tool to capture Kubernetes specific events that are happening in the cluster. It's somewhat similar, like I said, it's very similar to Hubble, but it's not as flexible or it's not as detailed as Hubble gets. That has been my experience playing with it. But if you really want to take it up the notch, there's another tool that's called PTCP dump. And what this does is something like this. Okay, so you can actually do kubectl specific captures, but then when you download the PCAP, you get packets that are annotated with process IDs, parent IDs, container name, pod name test. And this contains sufficient metadata. That this contains sufficient metadata that allows you to troubleshoot like Kubernetes specific constructs, essentially. So like in typical TCP dump, you're not going to get container name, container ID, container image, or labels or whatsoever. But again, like just as it goes with these with as security engineer, I feel like compelled to inform you use these eBPF tools with at your own risk or anything like because they do require significantly high privilege. So I don't like I personally don't feel comfortable running any third party like eBPF eBPF programs in production cluster. But the ones that are on eBPF.io, for example, they are vetted. It's again cert expired. So if you go to eBPF.io, once their cert is fixed, I see a hand raised.
Yeah, hey Kapil, it's me again.
Yes.
So have you there's also a tool called StratoShark. Have you ever tried that?
Yes, I
It's
have.
it's
Yes.
it's from the Wireshark developers.
Yes. Yeah. So StratoShark is interesting, but it does not capture packets. StratoShark captures syscalls, but it gives you a Wireshark-like UI. And what underneath the hood, what it does is this thing here. Let me show you. If you go to DRA iOS system, underneath the hood, it uses the same binary. It uses the same library that is used by Falco as well, which is used by Sysdig CLI as well. And so what you do is if you go into their wiki section, they have something called chisels, for example, right? And what those chisels are just like, the CLI or the special flags, and based on that, you can filter specific syscalls without being a strace wizard, without being a syscall or a kernel wizard, if that makes sense. Yeah, so it'll give you like all the metadata that's happening inside the Linux kernel. And this is again built on top of the libraries that have been created by people at Sysdig, who are also creators of Falco and also creators of Wireshark. So that's basically all I had to present. Like, I didn't really have a whole lot of time to prepare the whole slide deck and all those things. So, but any
All
other
right.
questions?
Yeah, thanks so much for going through that, couple. So everybody is unmuted. It looks like Itayo was typing something in as I was saying that. So I'll answer or I'll speak your question, Itayo. What are the best practices for auditability and cybersecurity incident handling in regards to egress traffic, especially with the ephemeral nature of the pods? Network addressing and historical data. Is this something that is enabled by default or requires hardening?
Oh, okay. So for capturing traffic, you're saying, right? For capturing flow traffic, or I guess capturing egress traffic. So Hubble actually has an expression filter that you can provide and say, I want to record all the egress traffic, or I want to record all inter namespace traffic or whatsoever. And so as I was showing, like Hubble has a CLI, and within the CLI, if you like look at one of their flags, one of their filters, you can filter that out and dump that into Splunk essentially, and or your favorite CM of the day. Does that answer your question? But no, one more thing for auditability, Kubernetes actually has a audit API. So if you go to Kubernetes audit logs, there is an audit API that is available but needs to be enabled here. But like if you go to your favorite Kubernetes distribution, whatever that is, like if you look at K3s documentation or RKE2 documentation, how to enable the audit API endpoint is going to be specific to that Kubernetes distribution.
Okay, does anybody have any other questions? Talia has one more. I see they mentioned debug task, but is it recommended for production environments?
No, I wouldn't recommend. I wouldn't enable debug. Um, wait. When you say they mention debug tasks, oh, who mentions debug tasks?
Auditing.
Oh, audit logs. No, I wouldn't recommend enabling debug endpoint per se. Um,
All right. Does anybody have anything else? All right. Well, thank you so much, couple. Italia says the link you provided for auditing is related to debug, correct?
oh, yeah, yes. Okay. Link is related to debug. No, that is not necessarily related to debug. That is related to security auditing, essentially. So any traffic, any kind of HTTP request going in and out of your cluster, any request hitting your Kube API server will basically be available for audit purposes. That is not your debug, like your developer debug.
Okay. I think Italia's good. Okay, well, thanks everybody, and thank you, couple. If you can send me a link to your slides, I'll make sure that those get posted along with the video. And just for people who are still here, next week's talk is going to be from Vinay Sawal from NERSC, and he is going to be talking about InfiniBand, which was a bit of a user request, because I think that a lot of us traditional network engineers don't know how that works. So thank you all for attending, and hope to see some people next week.